Welcome back for the second part of the lecture on Monte Carlo integration for rendering. Remember our declared goal last time, which was to find a way to do a cosine weighted integration of incoming light at a point over the hemisphere with respect to solid angle. That's quite a mouthful, but with the tools from last time and some more in-depth application details we covered today, we will be able to do it. The fact of the matter is that the solution to do it will only involve a few lines of code, and you will easily be able to find the corresponding instructions in the upcoming slides with little effort. But we still hope that you are willing to also pay attention to the theoretical background in case you ever need to dig deeper than the most basic rendering routines. Okay, let's get to it. Before we move directly to the hemisphere, we start off with a small step in the right direction, that is sampling the unit disk. Imagine that we have a disc-shaped surface and we can measure the light that arrives at each point as an RGB color. Now, in order to get a measure of the full light that the disk receives, we want to sample and integrate over the surface. To start off, we will want to generate uniformly distributed samples in 2D, but this time there is a catch. We want to distribute samples evenly on the surface of a unit disk with radius 1 instead of a rectangular area as we did before. For rectangular areas, we saw that we can just take two independent uniform variables and sample them separately. It is not so simple for the unit disk. For now, we know that the surface area of the unit disk is of size pi, so we will keep that information in mind. From last time we know if we can uniformly sample a domain, then the Monte Carlo integral is a simple average times the volume of the domain. But if we simply draw samples from uniform variables in x and y, we cannot cover the circle of the disk precisely. If we try to sample the space inside the circle with a rectangular area, then we're losing information because we're not covering the entire surface of the disk. If we want to instead enclose the unit disk in Cartesian coordinates, we can take a rectangle in x and y from coordinates -1 to 1. But inside that 2 by 2 rectangle, the unit disk only occupies an area of pi. So we will necessarily be placing redundant samples that land outside the disk. Since there is no light measured outside of the disk, those samples are worthless. Now, this is actually not that bad compared to losing information. In fact, this is one suboptimal way to do sampling for Monte Carlo integration. If we know how to draw samples from a superset of the locations that we actually want to sample, we can just throw away samples that land outside. And this is called rejection sampling. If we want to distribute samples according to a function f of x, but don't know how to do it exactly, we can apply rejection sampling if we know a function that works as a PDF p of x, such that p of x times a constant c completely encloses f of x. For distributing samples according to f of x, we can then draw one sample from a canonic random variable and one sample xi from the distribution p of x. If the canonic random sample multiplied by c times p of xi is smaller than f of xi, we accept the sample. Otherwise we reject it because it does not lie under the curve of our function f of x. The rejected sample then simply doesn't count towards n for the Monte Carlo integral. For a more visual interpretation, we check if a uniformly random point under c times p of x is also under f of x, and if it is, we accept it. Hence, with this method, we can get a distribution of samples according to f of x if we know how to sample its enclosing c times p of x. For integrating over the area of the unit disk, this could look like this. Since the unit disk ends at 1, we use an indicator function for the distribution for the circle that is 1 if the square root of x squared plus y squared is less or equal to 1, and 0 otherwise. The corresponding p of x can simply be the 2D uniform distribution from -1 to 1, so we know that the proper PDF is 1/4 everywhere, and we can choose c is 4. And this is definitely a method that you can use, for instance, if you are unable to use the inversion method. But in general, we will want to avoid wasting samples if we don't have to. So since we don't want to waste samples, let's find a way to generate inherently uniform samples so that we don't have to throw away any of them. There are other ways to sample a 2D plane other than what we saw up until now with Cartesian coordinates. We have another coordinate system that is also two-dimensional, but where we can easily limit points to a disk of given extent. We're talking about polar coordinates. Polar coordinates around a given origin are defined by a radius r and angle theta in the range from 0 to 2 pi. For the unit disk, we will use a radius of 1. The transformation from polar coordinates to Cartesian coordinates is as follows. X equals r times r, the sine of theta, and y is r times the cosine of theta. So this seems like a step in the right direction. Let's just try to generate uniform samples in polar coordinates, where samples can be naturally limited to a disk by a maximum parameter for r, and then convert them to Cartesian coordinates to get points in x and y. Let's try this right away. And below you have an example of how this could be realized with just a few lines of C++ code. Except the result that we get is unfortunately not exactly what we wanted. Uniformly distributed samples in polar coordinates are not also uniformly distributed in Cartesian coordinates. Since we wanted to sample the surface area uniformly, this distribution will not do because samples clump together at the center. And as we saw last time, if we treat a non-uniform distribution as if it were uniform during Monte Carlo integration, we will get the wrong result for our integral. So how do we fix this? You can pause the video here and take 5 minutes or 10 to try and come up with a solution for yourself if you like. Okay, so let's take a step back, think about the issue again, and try to solve this smartly. We know that the area of a disk is r squared times pi. Consider a sample budget of n samples and try to distribute them evenly over the surface of the disk. If we interpret the disk as many slim concentric rings of width delta r, then the inner j rings up to radius j times delta r should contain rj over r squared times n of the grand total of n samples that we are using. We can invert this figure to find that if we want to distribute samples uniformly along the radius, then the ith sample should lie in the ring that covers the radius r times square root of I over n. Since we know that the order of samples along our domain axis doesn't matter in Monte Carlo integration, we could swap the coordinate I over n for a canonic random variable, and we get Ri equals r times square root of the output from a canonical random variable. We don't need to make a change for theta because we saw that the distribution doesn't vary at all with the angle. So let's make this change, and if we implement it in our code the way we described it above, instead of uniformly sampling r, we compute it as the square root of a canonical random variable times r. It works indeed, and it is not even a bad way to arrive at the correct solution for uniformly sampling the unit disk. However, if you pursue rendering into its professional domain, you will find that you won't be able to derive the solution for other sampling domains so easily. You can take the solution and apply it and it will work fine, but we will show you a more formal solution so that you also have the necessary tools if you have to solve more complex tasks than this. So what follows is a formal method to achieve uniform sampling of random variables under transformations. Right away, let us convert a regular grid from polar to Cartesian coordinates. What happens if we do that? We can see that some squares in the grid are squished together while others are expanded, depending on where they are in polar coordinates. Remember when we interpreted the reciprocal of the PDF as a transformation of hypercube volume? So we can see that the transformation from polar to Cartesian coordinates seems to have a clear effect on the PDF. And we can make this even clearer. The PDF of an unknown sampling procedure is actually quite easy to visualize. All you have to do is subdivide your domain into bins, generate a number of samples, and then count how many of them end up in each bin. Optionally, you can normalize the counters to get the actual density values for each bin. Note that by making it discrete in this way, what we see is technically a probability mass function now rather than a probability density function. But for an infinite number of bins, they are the same. What we see confirms what we saw earlier. After transforming uniform samples in polar coordinates to Cartesian coordinates, the density is much higher at the center of the disk. Now our goal is to find out exactly how the PDF changes if we transform samples from polar coordinates to Cartesian coordinates, because we started out with something that was uniform and after the transformation ended up with something that was not. So if we can quantify this effect, we could use it, for instance, to weight samples during Monte Carlo integration, because we know the actual PDF, or we could compensate in the sample generation in polar coordinates so that they will be uniform after they are transformed. Assume that we have a random variable capital A and a bijective transformation T, whose input is the variable capital A and whose output is another random variable capital B. The conversion from polar to Cartesian coordinates is such a bijective transformation. If the transformation is bijective, this implies that the output of T must be either monotonically increasing or decreasing. This in turn means that we can find a unique output value for every input value and vice versa. Consequently, we find that the output of the CDF of the transformed random variable for a transformed value T of A is equal to the CDF of the original random variable capital A for a value A. So that leaves two possibilities for the output of the transformation. It can either increase with the input or it can decrease with the input. For instance, if the output of the transformation is just the negative input. In both cases, we have an equality for the change in the CDF of the output values over a change in the input values, and the change in the CDF of the input values over a change in the input values. The term on the right is just the derivative of the CDF for A, and we know the derivative of the CDF is the PDF. For the term on the left, we can use that the change in the CDF is equal to the PDF times the differential, so we get P capital B of B times dB over dA equals P capital A of A. We take the absolute value for dB over dA because the differentials could be going in different directions if, for instance, the output of the transformation is just the negative of the input. But since we want to find only the amount by which the PDF changes, and PDFs must always be positive, we take the absolute value of dB over dA. Taking the reciprocal and moving the term to the right, we get a formula for expressing the PDF of the transformed random variable as a change in the PDF of the input variable. Let's try to find an intuitive interpretation for this equality. The PDF of the output value, B, is the PDF of the input value, A, times dB over dA reciprocal. Now, based on what we have done before, we can interpret this term in two ways. We can either see it as the change in sampling density at A if we transform by T, or the inverse change in the volume of an infinitesimal hypercube at location A if we transform A by T. Try to make some sense of the latter interpretation because we will return to it in a minute. Okay, so we know how to establish the relationship between different PDFs after transformation, so we can go ahead and try to apply this to the unit disk. But we soon find that our tools don't work here yet because the transformation is not a function of just one variable, it's a function of two variables. So in order to quantify the change in the PDF in this multidimensional setup, we must find a solution that takes all involved variables into account simultaneously. And we can do this by moving from individual values to handling matrices of random variables. We can collect all of our individual single output variables into one multidimensional random variable. The output from such a multidimensional variable is a vector. If we do this, then we can just take the equality from before and replace the PDF of capital A with the joint PDF of the multidimensional variable capital A arrow. And the same goes for the output variable B. But for the actual change in the PDF, we have to look at the term that before was the inverse of dB over dA, or dt of A over dA. We now have to make sure that this term incorporates the full change of the joint PDF when we transform one multidimensional variable to another. This is where we have to introduce or recap, if you already know it, the Jacobian matrix. If we have a transformation from vector A to vector B, the Jacobian matrix contains all combinations of partial differentials for the individual values in both vectors. Therefore, the Jacobian matrix contains the values of all possible partial derivatives that we can form with vectors A and B. So if we take the first row and first column, the entry indicates how the first value of vector B changes with the first value in vector A. In the second row, first column, we see how the second value of vector B changes with the first value in vector A, and so on and so forth. Basically, the Jacobian matrix in our application encodes for a given location vector A how each transformed single output variable changes with each untransformed single output variable. The first column indicates how all transformed single output variables would be influenced by infinitesimal changes in the first untransformed single output variable. The second column indicates how all transformed variables would be influenced by infinitesimal changes in the second untransformed variable, and so on and so forth. If we again take the help of our imaginary infinitesimal hypercubes, we could say that each column of this Jacobian matrix shows us how the edges of an axis-aligned hypercube in our input domain change during the transformation T. And this is interesting because it means for any given position vector A, we can see the Jacobian matrix itself as a transformation matrix that is valid only for an infinitesimally small region at position vector A. The final piece that we need is the determinant. If we are comfortable with seeing the Jacobian matrix as a locally valid transformation matrix, then we can quickly quantify the change in volume that it generates. The columns of a square transformation matrix can be seen as the basis vectors of the transformed space. With this interpretation, the determinant of a matrix computes the volume of the parallelepiped that is formed by these basis vectors. So we are going to replace the term of change in range from earlier with the determinant of the Jacobian matrix, or the Jacobian of T for short. This gives us the change in volume of an infinitesimal hypercube at a multidimensional location if we transform it with transformation T. This is exactly what we have been looking for. Now, if this made your head spin a little, that is totally fine. Feel free to revisit this part of the lecture because it is definitely a tough concept to grasp. You don't need to remember these steps to apply the techniques that follow, but we wanted to show you the underlying idea and some reasoning for why it makes sense to use the reciprocal of the Jacobian to quantify the change in the PDF rather than just give you the final formula. Returning to the unit disk, let's see if we can now measure the change in the PDF caused by the transformation from polar to Cartesian coordinates, this time with multidimensional random variables. We can easily find the Jacobian matrix of the transformation by computing all partial derivatives, and if we take the determinant of the resulting matrix, we get radius r. So we have equality, the PDF of x and y is equal to the PDF of r theta over r, or p of r theta is equal to r times p of x and y. What this tells us is a uniform density distribution in Cartesian coordinates x and y must be proportional to r in polar coordinates r theta. And we can quickly check if what we computed here is correct. We can use this equality to simulate the PDF after the transformation. I have written a little script here that does exactly that, and it seems like our efforts paid off. We can very accurately predict how the PDF changes if we apply transformation T. I have provided the script that I used on the next slides in case you are interested or want to try something similar for yourself. The last challenge we need to face before we can finally solve the unit disk is the correct sampling of a joint PDF. Last time we only saw distributions from independent variables. We knew their individual PDFs, so we could simply invert their CDFs and sample them separately. But this is an assumption that we should not make in general, and there is a proper way to do it that only requires a little extra effort. In the case of two variables and given their joint PDF, we can do this as follows. We first compute the marginal density function of one of the variables and then the conditional density function of the other. We will use these marginal and conditional density functions instead of the PDFs for individual variables last time, because that is only guaranteed to work if they are independent. But the steps we need to perform on them afterwards are the same as before. Integrate them, invert the indefinite integrals, and use them for sampling. If we do this, it basically equates to a procedure where we first sample one of the random variables and then sample the other, because the second variable sampling might depend on what was returned for the first, hence conditional. How do we get these marginal and conditional density functions? We will look at the case for two variables here. You might have heard about marginal probability already. If you have multiple variables that define your outcome, the marginal density function of a variable is the probability density function for that one variable alone. We don't care about the values of the other. So for example, if out of all possible combinations of x and y, we have a 50% chance of seeing x equals 1, then the marginal density function for x based on p of x and y will be 0.5 for x equals 1. You can also see a variable x's marginal PDF as the function that tells you the average density at a given value of x over the entire range of the other variable. There is an easy way to get a closed form solution for the marginal PDF of a variable, and that is by integrating out. We do this by integrating the joint PDF over the full range of the other variable. The rules of probability tell us how we can get the conditional density as well. That is the probability of seeing a certain value y for a given value x. Once we have the marginal density function, computing the conditional density function is easy. We just divide the joint PDF by the marginal density function. For the sake of completeness, we also include for you here the procedure to extend this to more variables. We won't be using this anytime soon, but in case you were wondering how this can be scaled up, you can simply follow this method here. Okay, finally, let's apply all that we have learned and find a formal solution for uniformly sampling the unit disk. Now that we know all the steps, this will be really quick. We know that the sampling domain has a total area of pi, and we know that the PDF must integrate to 1 over the sampling domain. So we know that the density for any 2D point in Cartesian coordinates should be 1 over pi. We also know from before that if we want a certain PDF in Cartesian coordinates, we must multiply by r to get the corresponding PDF in polar coordinates. So we should use the PDF r over pi in polar coordinates for a uniform PDF in Cartesian coordinates. Finally, we compute the marginal density function for r by integrating the joint density function over the full range of theta and then the conditional density for theta given r. And from that, we already know what to do. Integrate the PDFs to get CDFs, invert them, and sample them to get samples for our custom distributions. Let's quickly check if it worked. And yes, in fact, we can confirm that this sampling method in polar coordinates gives us a uniform distribution in Cartesian coordinates based on the simple PDF testing procedure that we came up with earlier. So this is not really a surprise. The solution is exactly the same that we had before, but now we can confirm that both versions are equally correct. Something else that we can confirm now, even though we computed the conditional density of theta, it didn't actually change anything. We are still sampling uniformly from 0 to 2 pi, as we did when we first tried sampling the unit disk. But in more complex setups, this may not be the case. So it's best to stick with the procedure and compute the marginal and conditional density functions whenever you try to enforce a particular sampling strategy after a transformation. The final integral over the disk is just a formality because the samples are uniformly distributed over the area and we are integrating over the area. We can use the simpler Monte Carlo integration, which is just an average of the sampled RGB colors times the domain size pi. Now that we have mastered the unit disk, let's move on to the unit hemisphere. This is what we wanted all along, a way to integrate functions over the hemisphere surrounding a point in the scene to find out the total amount of incoming light. So instead of integrating over a planar area, we will now be integrating over the surface area of the unit hemisphere or directions in 3D of length 1 omega. But sampling in 3D space with the restriction that all vectors and positions must be of length 1 would be kind of awkward. We would have to throw away all the samples that don't land exactly on the surface of the sphere. So instead we are going to use a space where the surface of the sphere is a natural shape to get. And for that we use spherical coordinates, which are defined by a radius r and two angles theta and phi. Like with the unit disk, we have a transformation from one sample space to the other. The bijective transformation from r, theta and phi to x and y and z is something that we can easily find in a mathematical textbook. So we will use it to transform spherical samples into vectors. Again, we will look for a way to find a sampling strategy with geometric reasoning before looking at the formal method. We can define an infinitesimally small piece of surface area on the unit hemisphere for each direction vector omega. Each direction can be uniquely identified by spherical coordinates theta and phi. On the unit hemisphere, r always equals 1, so we can ignore it for now. So let's assume we want a solution for the integral over the surface of the hemisphere. How can we write this as an integral over theta and phi? Again, if you want to, take 5 minutes and try to come up with a solution if you care to. Remember that instead of a planar surface, we are now integrating over the curved surface of the hemisphere. First, let's define our setup. We have a planar surface that the point in the scene and the hemisphere rests on. The surface has a normal and the hemisphere is oriented around it. So the range of theta from normal to parallel covers exactly pi over 2 radians. Since phi covers the full circle, its range is from 0 to 2 pi. Again, we will try to disassemble the curved surface of the hemisphere into smaller parts that we can easily analyze, and then put them back together again. Let's assume we split the surface of the hemisphere along theta into ribbons of width delta theta. We keep splitting the ribbons and therefore delta theta gets smaller and smaller. In the beginning, the upper edge of each ribbon will be slightly shorter than the lower one, but the more we split, the smaller this difference becomes. If we split the ribbons infinitely often and delta theta goes towards an infinitesimally small number, this difference goes away completely. So after this many splits, the area of each ribbon is equal to its length around the surface times an infinitesimal delta theta. We can find the length of each ribbon by projecting it down to the ground. Using some basic trigonometry rules, we can then find the length of the ribbon as the circumference of a circle with radius of sine theta. The length of each ribbon covers the entire domain of phi, all the way around the hemisphere's normal. Also, we don't have a reason to expect that the surface area of the hemisphere changes between different angles of phi, so we can assume that the integral over phi is uniform. So if we want to write the found length of a ribbon as the integral over phi, we can simply make it range from 0 to 2 pi. That cancels out the 2 pi in the length of the ribbon, so all that we are left with is sine of theta. And with that, we already have the final integral over the hemisphere with respect to theta and phi. Now we have derived the integral of the hemisphere for theta and phi, but actually it is also valid for any arbitrary small region on the surface of the hemisphere. Let's look at an area on the hemisphere surface, delta omega, that we want to integrate over. We compare an integral over surface points omega with the integral with respect to theta and phi that we just derived. Since we can always transform theta and phi into a direction omega, it is okay to integrate the function depending on omega in both versions. Now if we compare the two, we see that the size of the integration domain and f of omega are the same. The result of both integrals must also be the same, so that leaves us with the conclusion that d omega is equal to sine of theta d phi d theta. Last time, we showed that if the transformation of a random variable is bijective, the result of the transformation is again a random variable and their CDFs must be equal. That means that their PDFs multiplied by the differentials must also be equal. So we can combine the equalities on this slide to get the relative difference between PDFs in spherical coordinates and over directions omega. Concretely, we find that if we want a particular PDF for our directions on the unit hemisphere, we must multiply by sine of theta to get the corresponding PDF for sampling in spherical coordinates. You can see that this is not as intuitive as perhaps our solution for the unit disk was, so it might have taken you quite a while to arrive at this on your own. Luckily, we have our formal way of doing it, and this is now much shorter. We use the transformation from spherical coordinates to points on the unit hemisphere. We have x is r times sine of theta cosine of phi, y is r times sine of theta sine of phi, and z is r times cosine of theta. If we compute the Jacobian of this transformation, we get the factor r squared times sine of theta. So we know that if we want a particular PDF for the distribution of points on the surface of the hemisphere, we must multiply this distribution by r squared times sine of theta for sampling in spherical coordinates. Notice that on the unit hemisphere, r is 1, so it has no effect, and we can ignore it moving forward. And that's it. The rest is now strictly by the book. We first find the volume of the domain, and we know the surface area of a unit hemisphere is 2 pi. So that means a uniform distribution over points on the unit hemisphere would need constant density 1 over 2 pi. We just saw how to convert a PDF for points on the hemisphere into a PDF for sampling in spherical coordinates. So we convert the PDF by multiplying with sine of theta. Then we find the marginal density for theta by integrating out phi. And we find the conditional density of phi given theta. With these two solutions for marginal and conditional density, we find their antiderivatives. To get a valid CDF for theta, we use a little trick. We add 1. Remember that this is allowed for antiderivatives. We can then invert these CDFs and get a sampling strategy for uniformly sampling the surface of the hemisphere with canonical random variables as inputs. And because we will be using Cartesian coordinates for our rendering routine, so basically x, y, and z directions for light and view rays, we transform them from spherical coordinates to points on the unit hemisphere in x, y, and z. One thing that we still need to consider here is we learned how to sample and integrate the unit hemisphere, but we did it with the assumption that our hemispheres will always be upright with the normal pointing in the positive z direction. We must be aware that the points that we will hit in the scene will lie on all kinds of surfaces with different normals, so the hemispheres we sample should be oriented likewise. This is quite easy if we store the normal, tangent, and bitangent for every intersection we find. Then we can just transform the samples to world space by multiplying our sample coordinates with these vectors and adding them together. Alternatively, if we have transformation methods available that do that for us, it is of course easier to use them directly. So let's take a short breather here, because we have just achieved a great deal. We now know how to sample the hemisphere uniformly, and with what we know about Monte Carlo integration, we can also integrate those samples to find the total amount of light that arrives at the surface point from all angles. After this much theory, we finally want to put it to good use. We are going to use what we just learned and add some basic lighting to our scenes. For now, we are going to focus only on diffuse lighting. Diffuse lighting considers only the light that is reflected by a surface in all directions equally, so there is no shininess or specular highlights. We will deal with those later. For now, we will only use diffuse light because we don't have to worry about material properties and other things, but can focus exclusively on using our new Monte Carlo sampling and integration tools. So remember the equation for reflected light from the lecture on lighting. We had an integral over the hemisphere with respect to direction omega, and we know how to do this now. Because it's diffuse lighting, we also know that Fr will be a constant factor, so no challenge there. The cos theta term should also not be a problem to compute. The question remains, what do we use for the incoming light function that we are integrating over, Li? And if we want to render realistic scenes with realistic lighting, this is a big topic that we will start to look into next time. For now, we are going to do something simpler. We will do two ways of lighting for our scenes that are easy to do. The first is ambient occlusion, the other is direct lighting. Alright, so what's the idea behind ambient occlusion? The ambient part refers to ambient light, that is, light that is just everywhere. Ambient is kind of a helper term to describe a basic level of brightness in a scene from light that seems to be in all locations. In the real world, this so-called ambient is always due to light rays being bounced around many times. But we know that we usually have shadows in tight corners or deep holes, and that helps to accentuate the surface shapes of objects. The way to simulate this is to consider every point in space as a potential ambient light source. For ambient occlusion, if we shoot a ray into the scene and we hit a surface point x, we then pick some random point in the surroundings of x and check if the path to this new point is blocked. If it is, that means that x is not getting any ambient light from this direction. For now, let's assume that whenever we shoot a ray through a pixel, we always hit the exact same point x. That means the more samples we take, the better our approximation of the integral over the hemisphere around x gets. So if we process a location x that is in a tight corner, then any of the surrounding points that we could look at will be blocked. So this method makes corners darker. If x is instead on the surface with nothing around it, then every surrounding point in its vicinity will be reachable, and if we hit x several times, we get the full ambient light. So at a visible surface point x in the scene, we can simplify the integral to integrating a visibility function over all directions in its hemisphere and checking if the point in direction omega at distance alpha can be reached without intersecting geometry. And of course, we must use the cosine rule for incoming light from different angles. And the constant factor that we use for Fr for now will simply be 1 over pi. So this gives us the simple integrand that we need for ambient occlusion. Here we see a summary of ambient occlusion again, and we also see what the Ajax bust looks like with ambient occlusion enabled. As you can see, surface details are highlighted because the ridges and tight corners can be identified by the shadows they receive. And this can be achieved by using this simple integral over the unit hemisphere with basic visibility functions. Of course, the way that we would do it now is by solving this with the Monte Carlo integral. And for a first solution, because we know how to do it already, you probably would want to use uniform sampling and corresponding integration. But this is actually a perfect opportunity to try our hand-at importance sampling. Remember that importance sampling works best if the distribution function for the samples mimics the signal. If we look at the signal we are integrating, we know that the term Fr is constant, and because we have no other information, in general scenes, we could assume that at any point in space, each direction has about the same probability of being blocked. So we could assume the visibility function to be sort of uniform if we consider all points in the scene. That leaves us with the cosine of theta, and it's clear that if a direction at a low angle theta is blocked, it will have a bigger effect on the integral than a blocked direction that is almost parallel to the surface, because that would hardly make a difference. So what we would have to do there is first find a sampling strategy that distributes samples on the hemisphere according to the cosine of angle theta, and then we use the PDF of that distribution during Monte Carlo integration. Now the PDF that you want is actually pretty simple because it must be proportional to the cosine of theta. So all you need to do is make that cosine of theta into a proper PDF that integrates to 1, as we have seen before. However, we haven't discussed how you can do cosine weighted sampling on the hemisphere. But you have all the tools now that you need to do it, so you are encouraged to apply today's methods to find a cosine weighted sampling strategy the formal way. But if you don't want to spend any energy on that, there's a quick solution called Mally's method. Mally's method gives us exactly what we want: cosine weighted samples on the unit hemisphere, and it's extremely easy to use. All we have to do is draw uniform samples on the unit disk, and we know how to do that already, and then project them up to the surface of the hemisphere. Done. The resulting sample distribution over the surface will be weighted with the cosine of theta. Why does this work? Again, we encourage you to invest some time in solving this yourself as an exercise. The second way that we look at today for getting some lighting into our scene will be through direct illumination from light sources. For each visible surface point X in the scene, we can just continue the ray in a uniformly random direction on the hemisphere, hoping to hit some light source. If the closest intersection that we find for a direction omega is indeed the surface of a light source L, then we can take the amount of light emitted by that light source L as the incoming light from that direction. And with that, we can already perform direct lighting. Again, the implementation for this should not be too difficult because all we need is uniform sampling on the hemisphere and integration around X. But it is kind of a trial and error approach. We are shooting rays in different directions and just hope to hit light sources by accident. Maybe we can be more efficient about this. And some of you might think back to what we heard not too long ago. We can sample the light sources directly. And this procedure that we saw in an earlier lecture is actually a special kind of important sampling. Instead of sampling and integrating over the hemisphere, we are sampling and integrating over the points on the surface of the light sources in our scene. That way, we don't have to randomly shoot rays and hope that they hit the light. We can take samples directly on the light source and see if we can reach them. Of course, we have to change our integration method a bit for this, because we must interpret the distribution on the light with respect to the hemisphere surface. So you might wonder how the change in the PDF for that looks. But this time the parts we need are already in the provided formula, and we derived them previously with geometric reasoning. Knowing what you know now, you may identify the factors in the back as the change in volume of an infinitesimal hypercube at a point y on the light surface if we project it onto the unit hemisphere surface. So these factors effectively take care of the change in the PDF from a sampled point on the light source to the corresponding direction in the unit hemisphere. To give the direct lighting the opportunity to add some color to the scene, we use the constant factor rho over pi for the factor fr. Below you can see how important sampling can make all the difference in the world. On the left, we use 100 samples per pixel. Each time we hit the surface point, we test one random location on the unit hemisphere and check if the corresponding direction leads directly to a light source. As a result, our output image is quite noisy, even after shooting 100 rays per pixel. If we sample the light sources directly, the noise quickly goes away. We are only considering those parts of the hemisphere that can actually lead to a light source, and therefore we get much more information from most of the samples. Another way to distribute samples, other than what we have seen according to functions, is to use so-called stratified sampling. If you paid close attention, you might have noticed that in some examples of uniform random sampling, we can get unlucky and end up with something that is not so uniform. But uniformity is good, especially if we know nothing of the integrand. Not regular sampling though, we already know that this is bad. So is there something in between? And the answer is yes. This is called stratified sampling. It is basically a hybrid of regular and random sampling, regular in the big picture, random for details. We subdivide a domain to sample into non-overlapping strata and then choose random samples inside each stratum. And this should look familiar to you because this is usually what is happening for sampling pixels. In the very first lecture, we briefly touched on supersampling and used it to resolve aliasing. Back then, we described it as a simple average. But now we know that this is actually an instance of Monte Carlo integration. And if you can, you should definitely extend your renderer to use this type of Monte Carlo integration with stratified sampling. Inside the bounds of each pixel, pick random locations and shoot corresponding rays into the scene. If you have a decent number of samples, compute their integral. If we distribute the samples uniformly over the pixel square and then compute the output color as the average, this is the simplest version of Monte Carlo integration for pixels, and it is called a box filter. We will see more complex alternatives in some of the upcoming lectures. One thing we need to remember though, before we said if we send rays through a pixel, we will always hit the same scene point, and therefore the more rays we send, the better will be the integral over the hemisphere of that point in the scene. But if we send our rays through different parts of the pixel, we will never hit the same point twice. And this may seem like a problem to us, but in reality it actually isn't. The Monte Carlo integral was an approximation from the start, because we can never sample all the points on the hemisphere, for instance. If we now add random offsets for the rays we shoot through pixels, all we did was add two additional random variables to the integral. So instead of integrating over the hemisphere at point x, we are now integrating over all the hemispheres of all points that can be seen with rays that go through each individual pixel. And this doesn't even make our code much more complex. For uniform sampling of these two new parts of the integral, all we have to do is apply the box filter on the color samples. The next slide shows you in pseudocode how this can be achieved. And this procedure may actually look very intuitive if you stop thinking about it as Monte Carlo integration of a multidimensional integral, but rather as an image operation. But we hope that you will soon be able to see it as either without too much discomfort. The last topic that we will cover here is the idea of low discrepancy series. This is in the same vein as stratified sampling. We may not always get the best behavior from truly random variables. It might be more effective to have something that seems random, but actually samples the entire domain with some guaranteed efficiency. And this is where low discrepancy series come in. Instead of the built-in true random number generators, we use these series especially if we need fast convergence. We are writing code for the GPU because GPUs are not very comfortable with random numbers, or we want a transparent and portable sampling behavior. And we are going to cover a very simple but very powerful example of low discrepancy series sampling. We are going to look at the Halton sequence here. The Halton sequence is a generalization of the van der Corput sequence, which is a 1D sequence that will always generate the next number between 0 and 1 that is furthest away from all previously drawn numbers, and it does so deterministically. It is based on the idea of the radical inverse. We can represent every integer with respect to a certain base with a series of digits that can take on values from 0 to the base -1. The everyday example of this is our own decimal number system, which has base 10. Every digit runs from 0 to 9, and we can define any integer by concatenating them. On the other end of the extreme is binary, which has base 2, where every digit can only be 0 or 1. But it's still possible to represent all numbers with binary as long as you have enough bits. For the generalization to arbitrary bases, we can write an integer as the sum of its digits times the base to the power of the current digit's position minus 1. For the radical inverse, instead of multiplying, we divide by the base to the power of the current digit's position. That means for every digit of the original integer, we now get a digit behind the decimal point, so it's no longer an integer. The van der Corput sequence is the result of repeatedly incrementing an integer and computing the radical inverse of it. In the range of 0 to 1, the van der Corput sequence for base 2 starts off with 0, 0.5, 0.25, 0.75, 0.125, and so on. The great thing about the van der Corput sequence is you don't even need to know ahead of time how many samples it will take to make it produce a good distribution. It keeps deterministically getting finer as you keep adding samples, and always hits the number between 0 and 1 that is furthest from all previously drawn numbers. In contrast to van der Corput, Halton works in arbitrary dimensions. If we have n different random variables or an n-dimensional domain, we must first choose n different co-prime numbers as bases for our sequences. For 2D, a very common choice is 2 and 3. The lower the numbers, the better. If we have data structures for storing integers with a given base and then methods for computing the radical inverse, the Halton sequence becomes very easy to implement. Whenever we need a new n-dimensional sample, all we have to do is add 1 to all integers and then compute their radical inverse. This gives us numbers between 0 and 1. And that's already all you need to do in the basic version. You can take the output of your Halton sequence and replace the random numbers you got from the standard libraries RNG to benefit from the quasi-random low discrepancy behavior. But there's one problem with this deterministic behavior. If you, for example, use the same bases and starting values for all pixels, you will quickly start to see unwanted patterns and perhaps aliasing in your renderings. On the right-hand side, we have a great example of how patterns can destroy your sampling strategy. Now, the distribution is somewhat uniform, but we can all agree that this is not a good way to cover the 2D area we have. So we should take care to make sure that we can avoid patterns as much as we can. We have two options. Option 1 is not that great, but can often be applied as a quick fix. You can initialize your integers to a random value in each instance. For example, if you have 5 random variables, then for each pixel you produce 5 random numbers with built-in functions and use them as the starting offset for the Halton sequence integers. The second option requires a bit more finesse, but should be hugely effective. What you want to do is, in each instance, for example in each pixel, you choose a random sequence that the digits will go through for each random variable. So, for example, instead of just going from 0 to 2 in the base 3 integer, you select a random sequence. At the point where you incremented each integer before, you now pick the next digit from the sequence. So when you draw the value from a Halton sequence variable of base 3 and the last digit is 2, you might jump back to 1 before you carry the increment to the next higher digit. This is the end of this lecture. We hope that we have given you a valuable set of tools to do some practical work with Monte Carlo integration. We also hope that you saw that these tools can be used when our common sense starts to break down. For example, when we want to do some advanced distribution on the hemisphere, etc. We have made sure to include short alternative explanations for the most important techniques that you will need, that is sampling the hemisphere uniformly and cosine weighted sampling. These two can already take you a long way, but at some point, if you pursue rendering, you will want to be able to apply other methods as well. And then it will be important to know how and why they work. And with that, we thank you for sticking around until the very end, and we also hope to see you next time.